I want to introduce, and then we're very excited to have our invited tutorial from SafeGraph. SafeGraph, as you know, is a leading data as a service provider. During the past year or few months, many of us have used data from SafeGraph for example, COVID-19 related mobility analysis. So today we're going to have this very interesting talk from SafeGraph on understanding consumer behavior with verified foot traffic data. The presenters will be James, Jeff, Eugene, and Michael. So guys, if you're ready, then the floor is yours. I will pause sharing.
Yeah, I think we're pretty, this is James. I think we're pretty much ready. Just checking in to make sure everybody's logged in. I see Jeff, I see Eugene, there's Michael. So yeah, we're ready to go.
Sure, yeah. So let me add Jeff or James as co-host so we can share. All right, so see if you can start sharing.
Right. Here we go. All right, so can everybody see the screen?
Yes, I can see that.
Okay, great. So we can get started then. So just a quick verbal round of introductions. I'm James. I'm the PL on the patterns team over at SafeGraph. And here with me today, as Gia mentioned, is Eugene and Jeff and Michael. Jeff is the product lead. Eugene is our star analyst that assists us in patterns. Michael is on engineer on the patterns team. We also have a new member of the team, Nisha. It's her first day. In fact, I think this is her first introduction to the team as well. So, this is a little quote. I'll just read it here. Unless your company is, one of the big FANGs or close to it, then analyzing all of your own internal data will only tell you about 0.01% of the world. And if you want to see beyond the scope of your company's pinhole into the world, you're going to need external data. You're going to have to bring that in and source it from outside. Right now, most companies spend way more on software than they do on data. And they also have more than 20 times the number of software vendors as they do data vendors. So Alexander Rosen, GP of the Ridge Ventures, mentioned that this is going to be really different in 20 years. I mean, data is where the richness of our business is based. And we're going to start seeing, shifts from, pure software engineering development into hybrids of data engineers and software engineers. I think we're seeing a lot of that already. So today, for the first 15, 20 minutes, we're going to kind of go through a little bit about who SafeGraph is, what our data is, where it can be applied. Then for the next 10 or 15, we can do notebook setups, dependency checks, just make sure everyone's environment is up and running. We have about 40 to 55 minutes of workshop when the topic of which is understand consumer behavior with verified foot traffic data. We're going to include a break in there, so when I get coffee or whatever, just a little break. And at the end, we'll reserve about 10 to 15 minutes to do Q&A to answer any general questions. So the key to what SafeGraph offers is that everything has a location, whether it's retail, real estate, and logistics, whether you're in marketing and advertising or financial services. They all have locations. You're either doing business forecasting, maybe you're looking at a trade area, or you're doing site selection, which is the topic for today. Or now you might do site selection for a cafe. Visit attribution, who's going where, when, location-based ads, the full gamut here. In the financial services industry, you're doing private equity, hedge funds. Maybe you're wanting to analyze businesses and the frequency of foot traffic that they receive in order to make forecasts on your financial models. The other thing is that location is dynamic. So, businesses open and close, they're always changing. They may make small changes to their names, Facebook to Meta. They may have addresses change, structures get torn down and rebuilt, they expand into new areas. People can move nearby or away. And of course, new places are cropping up all the time. And that's the core problem that we solve with our places product. So the problem with this is that the quality of location data is not easily available. And if you were to build like a full picture of all POI across the US, you have to resolve the questions for each of those individual locations, like latitude and longitude, the address that they have, what type of business it is, what category it falls into, of course, categories of subcategories, and what kind of structure type it is. Is it sort of like a mall type situation, or is it a standalone, an apartment tower, and so on. And so we solve this through about 4 kind of targeted products. I try to address each one of these questions that you might have about places. We have our core places product, which is a global product. We have I think we just reached our 10 million mark of places of interest that span the US, Canada, the UK, and we just went into sort of for premium brands and well-known brands, we're tracking them across the entire globe, so wherever they may be. The sort of a product that augments these core places is our geometry product, which we provide in the US, UK, and Canada. They are the geometries associated with those businesses. So, what is the footprint of the POI, and what spatial hierarchy exists with it. So a spatial hierarchy would be something like a theme park that has sub-parks within it, like a rides park and a water park. We track both of those geometries independently and the relationship between them. And we provide these in polygons in Wicked format, if you're familiar with those. Then we have the places and patterns product, which spans across the US and Canada. And it is an aggregation of foot traffic and location data with our POI, core places, and geometry. So we put all of those together to derive aggregated statistics of people visiting these POI across the US and Canada. And we also have the neighborhood patterns, again, and we focus on the US and Canada right now, the anonymized and aggregated mobility data between census block groups. So in this particular situation, what we're concerned with is the aggregation of movement between block groups. What block group did you come from? Where did you go? How long did you stay? And so on. So this gets a little bit into like, well, how do we build these curated data sets? They're machine generated, but human verified. What does that mean? Well, we do monthly updates to ensure freshness and accuracy. We have, various machine learning models at different stages of the data set building. We got some great engineers that are working on these problems every day. And we also provide detailed technical documentation, schema, bug reports, known existing bugs and whatnot. And all of that data is appended with PlaceKey, which is a new standard that we spearheaded for the community. First, we go out there with sort of an army of web scraping bots and generative models to sort of build the geometries, collect the data about the POI. We do this on a daily basis. But there's a second stage to that process, particularly for premium brands, where we have human beings that go over these geometries and we verify them and we make sure that the data that's available from various other vendors or publicly is in fact in line with what you would expect of the geometry. And they actually hand touch them up in order to make sure they're very accurate. We do the same thing with our POI data. We are constantly having people, real human beings that are going through the data, combing it and verifying it with other sources, in a sample matter, of course, in order to make sure that the quality of our data generation is high. So we have, we have an international expansion strategy. I mentioned already before that we have, our higher level patterns products that are in the US and Canada, but globalization is a major focus for us. We've, recently shifted away from like a country by country into a brand and category based expansion. And that's why our core places product is global, where we focused on those brands that people are most, concerned about, and simply begin collecting it globally. And that same strategy is going to begin to expand into our geometry and other products as well. So, specifically our plan is, start with the highest quality data on global brands, and then we layer in categories by region. So we would be looking at restaurants in South America, and which brands that we focus on is driven by customer demand. So, if you're a potential customer and you're interested in something we don't have, we take in that information and we can expand our product into it based upon that feedback. So now the course, our core product though, particularly in the US, covers, brands large and small. Again, with 10 million, POI, it's not like we're only doing the large brands that you might recognize. Within our data set, we have geometries, POI metadata about mom and pop shops, as well as the large franchises and international brands. And so, when you're interested in what's going on in a city or in even rural areas, we often have pretty good coverage of across the US. So site selection, we just have a nice little quote up here from Volta, SafeGraph's precision-based places data was crucial in allowing us to scale our operation and harness data-driven approach to expansion. And I included this slide because this is basically what our workshop is going to be revolving around today. We're going to take our patterns product and our POI product. We're going to create some geometric joins within the Seattle area to determine where those businesses are. And then we're going to generate a lot of statistical data that'll help us gain insights on where the best location for a new coffee shop might be. So modeling consumer behavior, again, this is how we're going to get really down into where a good coffee shop would be. We're going to start answering questions about how far people are traveling to coffee shops and how long they stay and where the foot traffic is to give us an idea of where we get a lot of exposure to our new business. And we can also gain insights into sort of the density of where existing coffee shops are to kind of reach that balance between exposure and oversaturation. Yep, this is just a quick blurb on where you can get the data. We have shop.safegraph.com, which is our web interface where you can kind of a la carte go through our products and select what's useful to you. We do provide sample data for free, so you can get an idea of the schema, the metadata, and the quality before making a purchase. So it's worth dropping by. And you can always reach out to our sales team. And for enterprise customers or people who have special use cases, we support delivery to AWS accounts. We support delivery to GCP. So arrangements like that can be made in order to facilitate whatever your company's internal data processing and ingestion needs are. And that's it. So this is just a mini Q&A that we've reserved if you have any questions about the product itself before we dive into the working session. And I'm actually going to go ahead and stop screen sharing, and you can put those into the Slack channel, or I guess just speak up, raise your hand, and we'll probably switch over to, I believe Jeff is going to be driving the workshop.
Eugene's going to screen share, but I will talk over him. But this is great. Feel free to ask any questions. There's a couple of different ways that we're monitoring. So we're monitoring the Slack chat, the Zoom chat if you have any questions. We're also in the Slack group, so workshop-spatial API. We also posted a link to a GitHub repository that's publicly available that will allow you to follow along at home. That's the notebook that uses SafeGraph data and uses, among other things, Sedona, which is something that we'll talk about as a package that's made for doing spatial operations sort of at scale. So that's the focus of what we're going to do here. And yeah, I think we should just dive in if there are no other questions. Cool. Eugene, you want to share screen? Are you able to? Do you have that permissions?
Yeah, I'm just pulling it up right now.
Sweet.
Jeff, can you see that?
And so, yep, I see it. And so we reserved like the first 15, 20 minutes here. If people are following along at home, please clone the repository, and then there are some pretty detailed steps here. Internally, we ran into some issues about dependencies and so on and so forth. So please run the make setup command to try to get your dependency set up. That should what that should do, in addition to having the notebook in the repository, is download a sample version of the SafeGraph dataset. So it's a sample of coffee shops in Seattle, monthly foot traffic data back to 2018. So the make setup file will download that file, make sure all your dependencies, your environments are set up, and so on and so forth. And then that should allow you to run the notebook. So we'll give people some time for that, but it's maybe a few minutes here. So if you do, if you're cloning the repository right now and then you're able to run it, please let us know in the chat if you're running into some issues. We'll be monitoring that as well. We can do that live, and so let's pause for that time for a sec here.
Yeah, and if you've already got everything set up, it's a good time to make that last coffee.
Yeah, we'll also be sort of just running through this notebook live as well. So I know sometimes people prefer to watch this, when they're going, when they're in their leisure. So we'll be able to watch. You'll be able to follow along with the notebook that's run now in terms of the plots, and we encourage you to, if now is not a good time, to follow along at a different time. But we do have this time set aside to walk through it. We have about, let's say, about 45 minutes to an hour of material. I mean, we expect to go through the code in the notebook in a lot of detail, but we can sort of go faster or slower depending on how people are interested. We have our first question. It's about Windows environment setup. It's in a Slack channel. Do you want to try to tackle some of this, James? What's the best way to get the make command set up on a Windows environment?
Well, this is going to be biased towards having some sort of Unix environment set up on your system. And Windows, I think it's been a long time, but maybe SIGWin. But I would kind of lean on the Windows users to know, kind of what they need for Java development. Yeah, I'm getting ready to chat with Sandeep here in the chat.
Is there anything else people should know about this before we sort of maybe dive in? Like, okay, so there's a make file. What it does is it makes sure all your dependencies are up, both in terms of Java, Spark, Python. Then it loads the notebook, basically, right? Am I missing anything, James, that people should know before diving in?
No, that's the gist of it. It is biased towards, Unix systems. If you're on Linux, I'm kind of assuming you know what's going on there, but we can certainly help, like, modify a couple of the commands. It's a little script. But on OS X systems, which it's been most tested on, well, it should just work. You did mention the dependency issues. We had an issue with on some Max Java home not being set. The most recent version of the setup script should account for that. But yeah, so if you're running into a Java error on Mac, then maybe doing a pull on the Git repo would be a good first step.
Yep. Cool. All right. So if other people have other questions, feel free to put them in the chat as well. But I think we should just dive in and start to talk about it. You want to share the notebook, Eugene? You're in the GitHub page.
There we go.
Awesome. Do you want to zoom in a little bit too?
Yes. Getting all my shortcuts. There we go.
I always just do Command plus. That helps me on Chrome. But so cool. So the way we've set this up as a team is so you're speaking to on this call people who work intimately with the SafeGraph data every day. And what we've tried to do here is sort of really put together a toy example so that you all can see what are different ways in which you can use the SafeGraph data to learn about different modes of working with Spark, learn about different modes, getting your hands dirty with the Sedona package, which, as I mentioned before, is for processing large amounts of spatial operations with SafeGraph data. And because we are, like, all of our data is location-based, all of the data that we have, can be mapped and can be plotted. Like, there's a lot of use. We developed these sort of examples that use SafeGraph data in this different way. So there's a toy example here. The context is that if you want to know about different locations, in this case, coffee shops in a particular area, you might also want to know about what are the visitors who visit these types of coffee shops and what is information about them. So as James mentioned, SafeGraph patterns data is an aggregation of mobile device data. So you can imagine your cell phone, a particular device will have, what happens is there's a location tracked for individual devices in our panel of devices, and then it's anonymized and aggregated to the places that they visit. So for example, if it were my phone, and that gets sent to, that gets anonymized, so the phone's data is not linked to me personally, and then the locations would be tracked over time. And then what we do is we aggregate those types of locations to points of interest, for example, coffee shops here. And so the flip side of that, if you're, say, if you're trying to cite a coffee shop, you may want to know information about all the coffee shops in a certain area. And so you might want to know how often visitors visit a place, where do they come from, where are they going? And this is particularly useful in lots of different types of applications. So the sample of data we're going to look at here is a version of our monthly patterns data set. So it's a monthly aggregation of all the visits to particular points of interest. And then there's a time series history of those visits. And so we have the sample here of, as I said, coffee shops in Seattle, and we're trying to answer questions that one would want to know when trying to understand what is the best location to place a potential coffee shop. And so broadly, the context for this particular notebook is trying to answer questions using the SafeGraph data, such as how far are customers willing to travel for coffee in this area? What types of locations receive the most visibility? And where do most of the coffee customers come from? And so this will be a sort of a joint partnership between me and Eugene here. Eugene will probably walk through the different notebook cells, and we'll walk through what each of the different types of what each of the different cells are doing. And then I'll jump in, and I'll probably, all of us will provide context here and there. So definitely follow along, obviously, but if you have any questions, we'd like this to be as interactive as possible. Either unmute yourself, interrupt us for sure, or post questions in the chat or on the Slack group.
All right, thanks, Jeff. So as Jeff mentioned, this is a bit of a toy example. As you might surmise, most of the heavy lifting that we do in terms of our spatial sort of querying and spatial processing really happens at the GPS ping level. For purposes of this workshop, we want to keep this lightweight. So we're doing a lot of things like in Spark and in Spark SQL that really we could just be doing in pandas and would, if anything, be quicker. But we want to make this, again, lightweight for this workshop and just showcase some of the things you could be doing. So you might see instances where you're wondering, why do this in Spark? The answer is you don't really need to for this, but this is sort of reflective of the things we're doing in much higher volume with much larger data sets in the background to produce this data set we'll be working with today. So with that said, I think we should get started. So as Jeff mentioned, we're just exploring some coffee shop data in Seattle. So the first few cells are just simple notebook setup, initializing your Spark session, running some import functions, including pandas. moving on from there, so the data set we're looking at is all of our coffee shops in Seattle and their monthly foot traffic visitation data from January 2018 to present. So it's monthly data aggregated at the individual coffee shop level in Seattle. And Seattle would define as just 3 counties in the Seattle area. You can.
Yeah, so SafeGraph data has a lot of, really just think of SafeGraph data in terms of rows and columns. And so SafeGraph has a lot of columns that are basically features or characteristics about the points of interest. One of them here is the category tags column, which for particular business types, in this case restaurants, allows you to, it's basically string filters for different, what the type of restaurant is. If it's a Mexican restaurant, a Chinese restaurant, in this case, we have a filter for coffee shops, and then that's how we're filtering for coffee shop rows in the SafeGraph point of interest data set. There's also similar ties to the geographic location of it. So in this case, the county in which the point of interest, or in this case, the coffee shop sits. And then we're just filtering for 3 of the most populated counties in Seattle, which we looked up ahead of time is these 3 numbers.
Yeah. So in this cell, we're just reading in our data. It comes in CSV form. By default, we're just going to read in all the columns as strings, and we're going to transform 3 of the operative columns for this workshop to the proper data types. So the ones we'll be working with are the date range start, which I'll show you what that field looks like shortly. We're transforming that into a date, as you might guess from the name. We're doing the same with the date range end column. And then we're transforming the visitor home CBG column into a map type column. It's a JSON column, so it's a little bit complicated, but we're transforming it into a map type here. So let's walk through some of the columns in the data set. So the first is the place key. This is the unique identifier for the coffee shops. It's not going to be the name, or it's not going to be the brand or anything like that. It's going to be the place key. So this is the unique ID for each coffee shop. SafeGraph's data includes a notion of spatial hierarchy. So when you see a parent place key, the implication there is that this Starbucks location is located within another building, and we've identified that building, and we've identified that spatial hierarchy. So in this case, we have this Starbucks, which is place key 228 dash, et cetera, which is located within inside place key ZZW, which maybe is an office building or a mall or a Target. We also have a strong concept of brands and branded locations. So you can see here that Starbucks is, of course, a very recognizable, well-known brand of coffee shop. So for that, we have a brand ID associated with it and a consistent brand name. So this makes querying the data much easier for our customers. But we also have lots of mom and pop, what we call long tail points of interest. So this is a coffee shop that we have not identified as a chain. Maybe it's a small local chain that we still haven't identified yet, but it might just be one location, so it does not have a brand ID. We'll skip past these for now, and let's move to those operative columns that we talked about earlier. So first thing you'll see is date range start. This is the month of foot traffic that we're looking at. So you can see that this date range start begins in July 2018 and continues through August 2018. So we can see that this row, if we're thinking about rows and columns, this row represents 1 month of foot traffic visitation to this given Starbucks location. And looking at the raw visit counts column, we can see that for this Starbucks in July of 2018, we recorded 329 raw visits to this Starbucks location. And when we say raw visits, we mean, we have a very explicit definition for that. We mean, given our panel of mobile devices, which ranges between 5 to 10%, as we understand it, of the US population, we saw in that sample 329 visitors, which we were able to attribute to this visit. So we just want to emphasize this 329 does not represent the real world true, quote unquote, true number of visitors to Starbucks. It's the number that we saw in the sample. And lastly, let's move to the visitor home CBG column, which here we go. This column is the one that we transformed into a map type column above. This is a representation of the visitors to this coffee shop and where they came from. And when we say where they came from, we mean what we understand to be their home location. As Jeff mentioned, we track devices locations over time, and we use that information to develop an understanding of where those devices' home locations are. So if we see, for instance, that my phone, let's say it's in the panel, is located at my address in Somerville, Massachusetts, every night for 6 weeks straight, we feel pretty confident that this is my home location. So we attribute my home location to be the census block group that my phone is located in for every night for 6 weeks straight. The algorithm's a little more nuanced than that, but that's approximately how we understand it. So we can say for this Starbucks location, we had 4 visitors come from census block group 53061, et cetera. And then if you explode out this column, which we'll actually do eventually, you'll see that this is a rather long, pretty long JSON array.
Yeah, and just to dial a bit on this visitor home CBG column, this is like a very useful column. And so it, like, even though it's one column in the data set, it's basically very long in terms of the amount of information contained within it, because it represents all, it's used quite commonly in something called trade area analysis, where you're looking at, for a particular point of interest, like a Starbucks, almost like the maximum distance that someone might travel to this particular point of interest, because it's the home locations of all the devices that have traveled here. And so we'll see, Eugene that this is particularly useful for understanding and characterizing different coffee shops, and it's used in different types of analyses.
Yeah, it's a great point. Yeah, go ahead.
I think the reason we picked CBGs here, census block groups, is often what people do is they tie the census information to the census block groups from which people go to these different points of interest. So if, for example, you might want to know, are all the people who visit my coffee shop, are they more from high income neighborhoods? Are they from sort of more diverse neighborhoods? What is the family makeup of those types of home neighborhoods? And so the reason it's census block group, which is the key for this dictionary, is because census block group is the smallest geographic aggregation at which the census reports this type of demographic information. So you might think of census blocks. This is even smaller. This is census block groups, which represent sort of hundreds, on the order of 100 to about a few thousand people in terms of population.
So let's move into some exploratory analysis with the data so we can actually look at it rather than just listen to me drone on and talk about it. So we'll load up some more packages. We'll be using GeoPandas, which is basically a spatial extension to the Pandas data frame. And then we'll be using Folium, which is a lightweight plotting and mapping package. So first thing to emphasize here is that we release our monthly patterns data on a monthly cadence. And if we're looking at several years of data at a time, our understanding and our knowledge of these cafes, irrespective of the foot traffic numbers, might be evolving over time. So for instance, we might know that there is Jeff's coffee shop located at some corner in Seattle in 2018. But as time goes on, maybe we gain some more nuanced information about it. So for instance, maybe we learn its office hours, its open hours. Maybe we improve our geocoding for that location because we got more address information. Things like that might change over time in addition to the foot traffic numbers. So here we want to make sure we have only the newest, the latest and greatest information for each cafe. So we'll write a simple window function partitioned by the unique ID, the place key, so each coffee shop. And then we'll order it by most recent date to earliest date in which that data appears in our data set. And we'll just add the row number based on that window, and we'll select the first row for each coffee shop. And from that, we'll select the information that we'll want for contextualizing the coffee shops on our map, which we'll see shortly. So here we care about, of course, the unique ID, the name, the brand, and then the street address, city, region, lat long, and the open hours. Again, we need to do this because this information might be changing over time. So if we just grab a random row, we might be getting stale information from maybe July 2018 when we have updated information in October of 2021. From here, we'll send the Spark data frame to Pandas. and then transform that into a geodata frame. And the process for doing so is very simple. We just create points from the longitude and latitude, and we create a geodata frame. Here's a function that uses Folium to plot this geodata frame. These are things that you can largely ignore. They're mostly for centering the map and setting the boundaries and for setting a base map. But essentially it loops through every row of this and plots the points and adds a tooltip with some of that helpful metadata we just went over. And then finally we can plot the map. So here's a map of all the coffee shops we have in Seattle, for which we have foot traffic information between January of 2018 and October of 2021. So we zoom in, let's say downtown. If I start getting my Seattle geography wrong, James, please correct me. But we can zoom in on, let's say, this Stumptown. We see that it has the place key, it's a unique ID. We have a location name, we have a street address, and we have open hours associated with it. So we know that it's open from 6 a.m. to 7 p.m. every Monday and every weekday. So this is a very simple map. It shows you, yeah, go ahead.
I think where's Pike Place?
Oh man, I think it's.
You remember probably here, right? Like the most downtown. Well, I only visited Seattle like a handful of times, and I've only been at Pike Place once, but I imagine it's here.
Yeah.
That's
It's
about
somewhere
right.
around
I'm actually on an
So-
island off to the left of that picture. but I do believe that's where Pike is.
Yes, it's around here somewhere. I remember looking explicitly at this example, and it'll actually come up. Oh, here we go. This is the original Starbucks, 1912 Pike Place, and this will actually feature prominently pretty shortly. So keep in mind this location.
Pretty good. Pretty good. Sorry to put you on the spot there. Eugene just like zooming around. Sorry.
No worries. I've had more live demo failures than that, so should be fine. All right, so that was some of the exploration, which was plotting the locations. We can move into the analysis, unless Jeff, you were about to say something.
I was gonna say, how are people feeling with are people following along with the stuff we've showed so far? Are there any questions? Okay, no questions. People used to tell me that if there are no questions, it either means we're explaining everything 100% and just so well, or people are not, or people are so lost that they're confused. So I hope it's the former and not the latter. But again, hopefully you see we're friendly people. Please let us know if you're having any questions.
All right, so let's move into some of the analysis. So the first question we want to ask is, generally, how far are people traveling to get coffee at these coffee shop locations? So the first thing that's helpful is that our data actually has a column that already has this pre-computed. It's the distance from home column, and it tells you the median distance traveled as the crow flies in meters between the coffee shop and the visitors to that coffee shop from their home locations during that time period. So if we move up here, and then here's where I have to try to find the column.
Right, there it is. You missed it.
Oh yeah, there we go. Here's the distance from home column. So to this given Starbucks, the median distance from the visitor's home locations traveled was about 5 kilometers, which seems reasonable. Like, I probably wouldn't be traveling more than 1 kilometer to get to a coffee shop, but given commute behavior and people from out of town, things like that, I think it's perfectly reasonable to have 5,000 people or be going 5 kilometers to go to a coffee shop as a median distance. So that we've already pre-computed. So we've already pre-computed this column, so we can just do a simple group by and find the average median distance over time. So here I'm going to move to my Databricks notebook, which just has some helpful visualization tools here. So you can see that there's a heavy right skew. There are outlier values in this column, and these outliers are likely due to some combination of one, coffee shops are located in downtown areas that receive high numbers of out-of-town visitors or commuters, and two, also just some quirks in the underlying GPS data. You can have ping sinks and things like that that tend to distort these values. So we'll just do a simple filter. We'll filter this value down to only visualize those locations with an average median distance from home of 25 kilometers or less. And then you could see that the distribution of values is much more reasonable. Most of the coffee shops, visitors are traveling somewhere between 4 and 7, maybe 8 kilometers to get there from home.
Yeah, I think that makes sense. I think the way we've defined Seattle here is the 3 most populous counties. So closer, it's not exactly the downtown core, but it's places where people might commute to. So the visitors from them to these particular coffee shops, is sort of higher, and sort of the distribution is such that it's not quite, people don't go immediately to the coffee shop like down the block.
Yeah. But in the case of something like a coffee shop, the distance from home column, one downside of it in a context like choosing a site for a coffee shop is that distance from home takes into account all visitors to the coffee shop, which as we saw above, can sort of distort those values. And when you're selecting a site for a coffee shop, you likely care more about local visitors. You'd want to optimize for people in the city, in the area, because most people aren't going to open a coffee shop except for maybe the original Starbucks that's going to bring many tourists or out of town dollars. And really you want to optimize for people in the area already, because coffee is not a higher order good. People aren't traveling that far. In order to get there, we'd have to recompute this column using only visitors from Seattle. But fortunately, we have Sedona, so we can do that very easily in Spark. So here we import Sedona, and then we register some of the Sedona functions so that Spark will recognize them.
Yeah, and if I can jump in on a little segue here on Sedona, there's a few ways that you can do these spatial joins. One of the most popular is with RDS trees, and that's what we were using internally before Sedona. But one of the challenges with it, it's a static tree once built. You can't add to it or modify it, and it's also not distributed in any way. So what we were having to do is sort of build this query tree and then deploy this very large query tree with 10 million or more POIs to all of our cluster, where it would be resident in memory on each one, in order to do these kinds of spatial joins internally. And what Sedona gave us is it's a fully distributed mode of doing this. So we were actually running up against real capacity issues, because now you're not limited by how many servers you can use, but you're limited by how much memory each server can have. And particularly with some of our more recent POIs, which are very large, national parks and things like that, basically it was just an unscalable solution to the problem we were trying to solve. Sedona solves this for us. Like Eugene mentioned, this is a relatively small data set, but there's nothing about this approach that couldn't scale to the entire country or world, using the tooling that we're using in this particular demo.
Yeah, the toy example is almost like embarrassingly small. It's like 66,000 rows or something like that. Where it's like, it's a little overkill to use Sedona for this type of work. So really, we routinely work on sort of millions of data sets joined to tens of millions or hundreds of millions of, or even billions rows data sets. And so that's sort of the mindset which we got into this, but we wanted it to run on your local machine. So it's a small data set for now.
So once we've loaded up Sedona, we'll read in the geometries for the Washington State census block groups. Again, this just comes in CSV form, and then we'll filter down the census block groups to the census block groups located in those 3 counties that we've chosen to represent the Seattle area. Once we're there, we'll use the wicket column, which is this is the original column in the data. We'll create a geometry type column using the Sedona function geom from wicket. So we're transforming a well-known text geometry column into a geometry type column in Sedona. From there, we'll just take the centroid for each of these. So we'll get a longitude and latitude for each polygon. And then here, because we're performing a distance calculation using one of Sedona's functions, we're going to transform this from a geodesic coordinate system into a projected coordinate reference system. So we'll just be using sort of the standard EPSG 3857. If you want to be a little more careful with this, you could probably use a projected CRS that's more tuned for the Seattle or Northern Washington area, but for now, we'll just use 3857. So for that, we can use the Sedona function ST_transform to transform this from geodesic 4326 to projected 3857. Then we'll rename a couple columns just so we can keep track of things. But the result is we have the census block group FIPS code, the unique identifier for every census block group. We have the original wicket column representing the polygon, the outline for each census block group. And then we have our newest column, which is the centroid for each of these polygons, transformed into a projected CRS. So you can see that these units are longitude and latitude in a polygon, but now we have units of meters distant from Null Island, which is 0, 0. And it's just going to be a single point representing the centroid. Any questions about what we've done here? Great, should be straightforward.
Yeah. Yeah, you're probably starting to understand that when dealing with spatial data, you have to be basically very explicit about coordinate reference systems, projections. There's a whole talk. We could probably go through this, but for now, just summarizing that, what we need to do is convert the data into the right type of format such that we can perform these type of distance calculations that respect curvature of Earth and so on and so forth. We have some materials for this if this is a little bit over your head, but this is just some pre-processing before we can go.
Yeah. All right, now we get into a bit of a meatier code block. Here we're going to be filtering down the visitors to each of our Seattle coffee shop to only those visitors that came from within the Seattle area. So that's the intent of this code block. We'll go through line by line, but again, we want only the Seattle visitors to our Seattle coffee shops. So we start with our sample, and then we'll explode the visitor home CBGs column, that JSON column that we went through earlier that shows the number of visitors that came from every CBG for which we have a recorded home location. We'll rename the key and value for these. So the key will be the census block group. The value will be the number of visitors. In this case, we'll filter out those CBGs with low visitors. And the reason we do this is because we add a jitter and we round up census block groups for which we have a low visitor count, just for privacy reasons, because if only one person came from a single census block group and we were to report that, it might make it easy to de-identify or identify that person. So for now, just to remove some of that differential privacy noise, we'll filter out those CBGs with low visitor counts. Here's where we do take the step of filtering down the home locations to only those located in the Seattle area. So again, we only care about visitor counts from census block groups that are located within those 3 counties. And then lastly, we'll aggregate it back up to each cafe again. So we'll take the place key, which is the unique ID for every cafe, and we'll take the census block group, and then we'll count up the visitors. So again, what we're aggregating is the number of visitors from each Seattle area census block group to each of our Seattle cafes over time. So between January 2018 and October 2021, how many people went from CBG A in Seattle to this particular Starbucks in Seattle? So that's the number we're generating now. Then we'll perform a join. Because notice that we dropped a bunch of our information for these locations in doing this aggregation. We'll perform a join with our data set from earlier that had the most up-to-date information for our cafes. So again, this is cafe latest. Hopefully the name's helpful there. And we'll just grab the latitude and longitude and we'll rejoin it to our aggregated data using the place key, the unique identifier for each location. And then finally, we need to do some geometry transformations. So now that we have these cafes, we have their latitude and longitude, and we have the number of visitors from each Seattle area census block group, we need to transform these cafe locations into a geometric form that Apache Sedona can recognize. So here we'll take, we'll transform each of these into, we'll add a geometry column, and we'll create points using the longitude and latitude. And then, as we did in the previous cell, we're going to transform these from geodesic coordinate reference systems to a projected coordinate reference system, the same one. And then lastly, we'll join it to our census block groups so that we can have a single data frame that has the geometry for each cafe, the geometry for each census block group centroid in the same projected coordinate reference system. And then we'll have the total number of visitors from that census block group to that particular cafe between January 2018 and present. All right, I think that was a big mouthful, but I'm hoping this visual right here makes pretty clear what we did. Again, this is a number of visitors over the last 3 years from this census block group to this particular cafe. And then we have the geometry information for each of them. All right, now we can move into our actual, yeah, Nisha, do you have a question?
Yes, I do. So this final data set that you have, for every place key, there could be multiple census block groups associated with it, given the map field that you showed us earlier, Eugene, right? So, yep. Okay, so this final 30th cell that we have in here could have multiple, like a single place key associated with multiple CBJs, and the number of visitors and or distance that we would calculate henceforth.
Yeah, that's right. So
yeah,
if we,
okay.
Let's see if we,
and that's because
you can see here, like,
yeah,
the first 5 rows are the same CBG. Here is the one ending in 006, and it's like the number of visitors from this CBG to these different coffee shops, which have different place keys here. So it's this particular table is all combinations of CBG and place key based off of exploding that dictionary. With visitors greater than 5, with the caveat that visitors greater than 4, and you only include rows where CBG is in Seattle.
Okay, thanks.
Yeah, I think all we're doing is like taking that dictionary, exploding it out so you have multiple CBG, each CBG place key pair is an individual row, and then filtering out those rows for CBGs that are outside of Seattle, because someone comes from New York, where I live, to Seattle, that would show up as a row here. So Eugene did this great group by here.
Yeah.
So in this case, we can see this one coffee shop, we have 1,100 known home CBGs. I have a suspicion that this is the Pike Place Starbucks, but don't quote me on that. But we have visitors recorded from 1,100 different census block groups in the Seattle area.
Fantastic, thanks.
Now we can finally perform our actual distance calculation. So we'll just calculate the distance using this very handy function, ST distance, between the cafes. Again, that's a latitude and longitude, and the census block group centroids on a row-wise level. So that'll give us the distance from home in meters between every census block group pair, every census block group and cafe pair. This is a bit of a sort of messy query. I couldn't figure out a better way to do this. So if anyone has any ideas, please shout them out and tell me why this is super inefficient. But essentially, I want to do a weighted median. So for each one, let's say we have 77 visitors between this census block group and this cafe, and we now have a distance between them. I want to count this distance 77 times, but this next one only has 5 visitors over the last 3 years between this census block group and this place key. So I only wanted to count this one 5 times. So here, essentially, I repeated every row based on the number of visitors between that census block group and that place key. I won't go into the details of how I did this because it's kind of ugly, but essentially I repeated every row so that we have that distance counted for the number of visitors.
The key there is that pause explode function, which is like our dictionary explode function, but based off of position. So you also see here, if you're newer to Spark, that in addition to using the Spark Python API, which is what Eugene has done for most of this, you can also pass in straight SQL to using Spark. to handle these distributed loads. So just some different flavors of using it to, if you're newer to Spark, that you can see and get used to.
So now we want to move into actually calculating this weighted median. So again, we'll create another window, this time just partitioned by the place key. And then we'll create our sort of function for calculating the median, which is just finding the 50th percentile. Let's see. Oh, I see. Okay, this is helpful to see. So this is the output of this ugly query here. So you can see that this pairing is no longer unique. We have one single place key, and then we have one census block group, and we know we have 77 visitors from there, and we have the distance, and then we just repeat it 77 times for purposes of calculating this weighted median. So then we'll actually calculate the median, group by the place key, and then calculate using this median percentile function up here over each place key. Oh, I guess I didn't use the window function. Okay, you can ignore that. And then we'll have the median distance traveled within Seattle. So you can see for perhaps this given place key, the median distance traveled by visitors from within the Seattle area is 5 kilometers, but this one is only 1 kilometer. So if we move back to the Databricks notebook, we can visualize this, and you'll see that this has quite a bit of a different distribution than the earlier ones we saw, where we had all locations. So this has a much longer right tail, and the values are much closer to 0, essentially. People within Seattle, when they visit coffee shops, are just going to their local shops. And this makes sense because we filtered out all the non-Seattle visitors, all the people who are just in town from New York for the weekend, hitting up the locals, like original Starbucks, things like that. And then here we calculate, this is a very simple group by, we just calculate the total visitors and the total visits for each place key over the last 3 years. This is mostly just so we can have some helpful tooltips and metadata later on. And then lastly, we're just preparing our plot for creating our final map here. So we'll take, here. Let's further this job. So the intent here is to essentially figure out the cafes that have the greatest delta between the median distance traveled overall, including all visitors, versus this new column that we just calculated, the visitors only within Seattle. And the intent here is to essentially understand sort of this trade area analysis that Jeff was talking about earlier, but basically which of these coffee shops are most dependent on out-of-town visitors and tourists versus which ones have a visitor base that's primarily their locals, the people who live on the same block or like a couple streets away. So we'll join the newly created column to our original data set where we calculate the average median distance from home using a pre-computed column. We'll filter out any cafes that don't really have a meaningful sample. So we just arbitrarily said, if you don't have at least 1,000 visits since 2018, we don't have enough data for you to make meaningful determinations here. And then from there, we can see sort of what that delta is. So we can see for this location, for instance, the delta there is almost is over 700,000 kilometers, or is over 700 kilometers, excuse me.
Yeah, so there's a lot of, because we track CBGs to their most common nighttime location, you'll get a lot of like, it's actually a really good column for understanding tourism. Like you'll see that a visitor to a Seattle coffee shop comes from New York CBG, and then that's what drives that skew.
And then from here, we'll say, yes. So we'll just choose the 500 with the greatest delta, and we'll call those the most touristy locations. And then we'll choose the 500 with the smallest delta, and we'll consider those the most local, locals only coffee shops. Here's another mapping function, and here we go. So the blue locations are the ones we understand to be the most touristy, whereas the red ones we understand to be the most local. So when you're zoomed out, it's a little muddled, but as you zoom in, you can quickly see that essentially the downtown locations tend to be the most sort of touristy or most reliant on out-of-town visitors, whereas the red ones tend to be visited primarily by locals. Of course, like it's locations are mixed in there a bit, but you can still see that that skew generally is present geographically speaking. And then if you go further outside of
Seattle, if you go to the south, in the South Hill Park, there's like an area where there's no tourist areas. I guess it's near the airport, a small local airport, but those are only traveled by locals pretty much.
Yeah. So this provides you with some amount of insight into, I guess, the types of people that are actually visiting your coffee shop. And if we go to the original Pike Place location, well, actually, I don't know if I can find it again. Yeah, here
well, it's definitely blue. Oh, you got it. Yeah, of course.
So this one skews quite a bit touristy because you can see the delta there is over 750 kilometers between the pre-computed column average and the one we recalculate ourselves using only locals.
So it looks like we finished a little bit early, but not too early. I wonder if I can throw you a curveball, Eugene.
Yeah.
Are we able to tell what kinds or brands of cafes tend to attract tourists versus locals? That should be in the data set, right?
Which brands tend to?
Yeah, like can we drill down a little bit on the types of cafes that are getting local versus?
How do we want to do this?
We're putting him on the spot here.
Yeah. Yes.
You have a column that's already the red and blue, right? Because you have this visitor type column.
Yeah.
If the visitor type already has brands in it, you could just do you could do it, yeah. And then let's do a quick time check. Well, let's not like zoom in. Eugene typing code. You can finish this, Eugene, and then James. So we're at 10, right?
Yeah. And we were reserving about 10 to 15 or so minutes for questions. So we have like a 10-minute buffer here. We can even take a break before questions or just go into questions, I suppose.
I thought this ended at. I thought we had till the end of the hour, or do I have that wrong?
We can let Gia chime in, but I'm looking. I thought I went to 10:40. Yeah.
Yeah, Jia or Yuchun.
10:40. So we have 30 minutes.
You can go to 10:40, right?
Yeah, 30 minutes.
You can go all the way to 10:40 actually, but if you want to take a break, that is totally fine.
I'll leave it up to you guys on what you want to do. Do we have a little bit more of the notebook to go through?
We do actually. We've actually gone painstakingly through the first question. So what we can do, maybe let's take like a 5-minute break because it's been a little bit, and then after that we can go through sort of the remaining questions, which will be kind of similar type of analysis. We can go through it a little quicker now. We've introduced Spark, we've introduced SafeGraph data. We can probably go through it a little bit. How does that sound to everyone?
Yeah, that sounds good. We can clock it now. We'll be back in, let's say 10:15, 10:16, around then.
Cool. Sounds good.
And so meanwhile, everyone, you can try to run the code. And if you have any questions, also feel free to pose it here. And then our SafeGraph people can help address those questions. And for people who just joined, we're taking a short break and we'll be back in a few minutes. And James, Jeff, Eugenie, whenever you're ready, feel free to resume.
Sure, thanks. Thank you, Eugene. If you wanted to, you can probably get started.
Let's do that. So I think James left me a challenge question, which I promised was not planted before this.
Or was it?
With which of the brands in Seattle have the most touristy locations? I guess if you want to get some work done in the cafe, which place you want to go to make sure that you get disrupted least often. So this is the query I ran here. So I think one thing I obviously should have done was done a filter for locations with brands with some more locations, so we got some more meaningful numbers here. It turns out Starbucks is not a bad bet. So only about a third of the locations in the Seattle area tend to be of the touristy variety. See, maybe if we like add in a filter here, let's say places with at least 3 of each type of location. So we'll let that run and then we'll come back to it later. All right, as Jeff mentioned, we did have a couple quick sections remaining in the workshop. I think we went into maybe excruciating detail in the preceding section. For this one, we want to do some quick hits with the data and doing a couple more quick spatial queries just to wrap things up. So the next question we had is, it's a pretty simple one. In what neighborhood do coffee shops tend to get the most visits overall? Basically, where is the most coffee shop visitation happening in Seattle? I think everyone might have a pretty good intuition for where this would be the case. Probably downtown areas where coffee shops tend to be located, but let's see if our intuition holds with this. So in this case, we'll read in a CSV with the geometry outlines for Seattle neighborhoods. And the Seattle neighborhoods are as defined by the city of Seattle on their OpenGIS website. So this is where that data comes from. Like before, we'll take that wicket column and we'll make a geometry type column. And then just to show it here, these are sort of undefined neighborhoods. So maybe I should have shown a different example here. But as that's running, let's see. Oh my God. In any case, this is a data frame with some Seattle neighborhoods and their shapes. Again, we'll just do this again, just for belt and suspenders. We'll take our cafes. We'll just take the latest version of them because we only need the one, and we'll make another geometry type column out of them, make them a spatial data frame. And then we'll do a simple spatial join. So here we'll select the cafes and the locations they're located in, and we'll do that with a simple spatial intersection. So we'll intersect the Seattle polygons with the cafe geometries. Notice here we didn't have to do any sort of transformations to the projection or coordinate reference systems for the cafes because we're doing an intersection. Had we been calculating something like an area or a distance, we probably needed to do that again, but here we could just skip that step. And now we have a map between each of the place keys in our cafes and the neighborhoods in which they're located. I'm glad these neighborhoods have more interesting names. So we can see like the Adams neighborhood is where this particular cafe is located. And then we also have the geometry corresponding to the outline of that neighborhood here. Next, we'll take the aggregated visit and visitor count columns, which we calculated earlier. Again, this is the number of visits and visitors to each cafe over the last 3 years. So we'll take the cafes, we'll take this mapping of cafes and neighborhoods, we'll join it to the total visitation, and then we'll group by the neighborhood this time and count where all the total visits and visitors were happening within each neighborhood. We'll move this to a pandas data frame, turn it into a GeoPandas spatial data frame. And then another very similar or very familiar mapping function. And then here we have a choropleth map of the neighborhoods in Seattle as colored by the amount of coffee shop visitation that happens within each one. So I think our initial intuition sort of holds here. As you would expect, the downtown areas tend to have a high concentration of coffee shop behavior. As you can see, these are in like the 90th percentile among neighborhoods in the Seattle area, in the downtown here. Maybe this area, which is primarily park space, ranks a lot lower just because there's a lot of less built environment here, a lot fewer coffee shops. You could also see the area, I believe, University District. This is the area around the University of Washington. As you would expect, there's also a high coffee shop visitation rate here.
And yeah, so we chose neighborhoods here, again, as sort of a contrived example. There's like, the goal here was to demonstrate the usefulness of Sedona to do this sort of spatial intersection, right? So you could intersect our points of interest, lat longs, with any sort of geometries you might want, right? We have built into our data set common ones, so census block group, census, and so on and so forth. So it didn't make sense to join to those, but you could imagine if you had your own neighborhood areas based off of custom work based off of your own site selection, you might want to do those types of spatial joins from our data set to another type of data set. And then this kind of code would allow you to do those spatial joins at scale really efficiently.
Yeah, it's Professor right. Within our own data set, perhaps one place where we're doing this most often, as Jeff mentioned, is when we're trying to calculate the common home locations for a given device. So we'll typically be doing a join like this for a series of GPS pings we receive from a given device, but we'll be doing it on a time series basis as well. So we'll be tracking where these pings are coming from a particular device in terms of their geohash 7s, I believe. So it's a pretty small area. It's about the size of maybe a bit smaller than a football field, something like that. So we'll be tracking all the various geohashes this device will be submitting pings from during a certain time of day over a rolling 6-week period. And we'll use that window to determine what we understand to be that device's common daytime location and common nighttime location. So again, here, this is a very simple toy example, but you can see how this would get complex very quickly with a much larger data set.
Yeah, to chime in a little bit, one of the pre-processing that we do is we identify first where visits occurred. And so that generates approximately 50 million a day in the US. There are more if you take our entire data set amount. And we do use Sedona and these spatial joins in order to determine what place did that visit occur. So first you just have a visit, which is like someone stayed in the same spot for a period of time, would be the simplest way to explain it. And that's like some lat long point on your map. And then we have to map those into whatever geometries make the most sense for them to visit. It's not as simple as a spatial join. We do the spatial join, and then there's some machine learning models in there that kind of tease out ambiguous situations in order to allocate the visit. But yeah, so it's perfectly capable of handling our data sets, which are 10 million different geometries and 50 million points in time every day.
And then the last example we're about to touch on was sort of the inverse of this question. And this part actually doesn't have even any spatial queries in it because we'll just be relying on our own pre-computed columns from here. But if in this section we were looking to which part of the city experiences the most coffee shop visits, I think naturally it's worth asking where is a place where that is home to the most coffee shop goers? Like what is the most coffee obsessed home neighborhood for people in Seattle, which I think is a good crown to own because Seattle is very famous for its coffee. So it'd be interesting to see what happens here. So I think whereas our intuition up here was it'd be probably downtown, certainly a denser area where workplaces and students are located. Here, you might suspect that it'll be the people going to these neighborhoods. So let's see how that turns out. So again, we'll start with our sample and we'll do the familiar explode on the visitor home CBG column. And then This time we'll just group by the home CBG, and we'll count the number of visitors that were present from that given CBG. So in this case, it turned out to be this particular CBG, 82001 is the census block group ID. And it saw 40,000 visitors since January 2018, which is just under about twice as much as the second place. So from here, we'll take that CBG, we'll take the top 1,000 of these CBGs, we'll join them back to the Washington census block group geometries that we saw earlier, and we'll transform this into another GeoPandas geodata frame. Here's another mapping function, very similar to the others. And we'll just plot these. And then here we end up with sort of a scattered, maybe modern artish type map showing where all these visitors are coming from. So I think you see a couple things. First, you see certainly some larger geometries, which makes sense. The larger the geometry, potentially the more people are located within it, but also the more spread out these locations tend to be, where people have to travel elsewhere to get their coffee. But you can also see that generally they tend to be on the periphery of the city, because a lot of these people might be commuting into downtown to be visiting these downtown coffee shops that we saw earlier. But you can also see just a fair number of downtown locations as well, because presumably there are plenty of people that also live downtown that are visiting these coffee shops as well. So you see sort of a bifurcation where you see visitation from downtown areas, but also sort of the suburban areas outside the city. I think that concludes sort of like the interactive code walkthrough part of the workshop. I think with respect to this example, we want to highlight some of the simple use cases and simple questions you could answer about coffee shop locations or retail site selection use cases that you can answer with our data. Just using kind of a toy example, but at a higher level, we also wanted to show that Apache Sedona really adds like a familiar and sort of straightforward spatial SQL API for performing distributed spatial queries. It'll be very familiar to anyone who's like worked with Postgres before, but certainly never on the scale of data that you might be processing otherwise in Spark. And yeah, we just want to show how user-friendly it is.
Great work, Eugene. Yeah, it's worth noting here that like a lot of the ways in which we implemented Sedona through these user-defined functions in Spark is basically identical to how one would do this without Sedona, from my understanding, right? It's just like a swapping in of a function that comes from a different package. Is that right?
Yeah, the names of the methods and functions on the joins, or I hate to use the word standardized, but they're common amongst various geometric query engines. And I did want to sort of, verbalize the question that was in our chat and said, is there any information, this is from Vishnu Mahesh, is there any information in SafeGraph data about purchases? For example, what percentage of visits to a store resulted in purchases? This is a question we get asked a lot. And because of that, we are actively working on providing our customers with this particular data. We expect to have this kind of information begin making its way into our data sets in a couple of months by first quarter next year.
That's great. Yeah, so that's the end of that session. Again, if people have been working on this, feel free to chat. We have us for a while. We'll be in the Slack group as well if you have this at a later date. Sounds like I looked at the schedule. We were up for Q&A here. Is that right?
Yeah, that's it. And just to fill a little bit of the airspace, we will be in the the SIGSPATIAL chat, of course, but we also have a public community chat for SafeGraph itself. So for those who are data curious and would like to download samples and have questions going into the future, we're always hovering around in there as well. Which I can dig up the link actually and put it in our chat.
I have it, yeah.
All right.
What Jane is talking about is something called the SafeGraph community. That's what you're talking about, right? Yeah.
Yeah.
It's a Slack community, but also a discourse, a forum for people using SafeGraph data, predominantly in academic settings, but increasingly people who work in data science and industry. So there's a lot of really good material there for nuances about the SafeGraph data, how to work with different columns, code snippets, examples, documentation. It's about 15,000 strong folks who are working in this. And if we didn't mention it at the beginning, SafeGraph data in particular has been used in over almost hundreds of academic publications at this point. I don't know if we've reached 1,000, but definitely hundreds at this point across economics, social science, health, lots of different sort of interesting mathematical modeling kind of studies, you name it, right? Especially during the COVID pandemic, we made data accessible, freely accessible to academic researchers and people working on the COVID problem. If you are affiliated with an academic institution right now, you can get access to SafeGraph data for free. So it's a fun way to explore and understand. So highly encourage you to join that, join the SafeGraph community as I've linked there. And it's a great just resource and just continuing the conversation to the stuff we've talked about today.
Awesome. So any questions from the audience? So if there's no question, I have one. Like you mentioned, in the past year, many people have tried to use the data for COVID-related analysis. And so from my experience, a lot of people might be interested in understanding how they can reduce the selection bias that's potentially in the data set. For example, now the data is mainly from mobile phone users. But I know there should be some methods that can correct that selection bias to some degree. So if you have any recommended measures that people can use to do that, that may be very helpful.
For sure. Yeah, I think one thing people have done, and there's a couple of different published papers that have been published on this. There's like a group, the Costin et al. I think it's like Carnegie Mellon and Stanford, that recognize that because our visits come from a panel of mobile devices, what they call coverage. So the proportion of visitors that come from our panel divided by the proportion of true visitors, which is unknown, varies depending on the point of interest. As you say, like the amount of true visitors covered by our panel varies depending on the point of interest. And if you extrapolate that out, that could lead to some biases depending on your application. Now, I'll say it really does depend on the type of application. That paper that I referenced was mainly used, as you can imagine, it's hard to have some ground truth data. So if you don't have ground truth data, it's hard to correct for that type of bias because you don't know how you're correcting. That said, we do have some approaches we have some publicly available notebooks on our website. So if you go to docs.safegraph.com and go to the data science resources section, we have a lot of Jupyter notebooks like the one Eugene showed you today that in particular allow you to upsample visitors to a particular point of interest based off of the home locations that we have for those places. So as you might imagine, you can look at the home locations of all the visitors that we have, and then look at the population of those homes and to see how well are we sampling across the different types of home locations that we have. And so you can do this at the census block group level. That can be a bit noisy because census block group geographies vary, but we also recommend doing so at the county level or the state level. Then that can help alleviate some of this bias. We actually did in the SafeGraph community have a session on this. We call it normalization, which is in a supplementary file that we provide as part of SafeGraph data. We provide basically daily statistics on how large the panel is and what is the geographic dispersion of that panel. So you can see whether certain areas are overrepresented or not. And so it's something that we do recommend, especially if you're looking at time series data or have an application that really the panel size really matters. So I highly recommend to look at those types of applications and those types of materials we've made available.
Yeah, no, and the selection bias, the sampling bias, these are things that we think about a lot. It's not like a one-off thing. We're actively looking always for new data sets to augment what we have, new ways of normalizing and new public data sets that we can use to augment and reduce that bias for our customers. So it's always worth checking in to see what we might have coming out on the horizon as well. It's something I think we revisit it like at least every quarter or two. Like there's usually some amount of project where someone spends a significant amount of time thinking about these problems.
For sure, that's
for sure. No, go ahead. Oh, yeah, I was mainly going to say that, like, yeah, the best use of SafeGraph data is to understand it as a sample of the true visits of the underlying population, and then to think about what sort of signals come out of that sample. I mean, I'm speaking to, I think, a primarily academic community here, so people who understand sampling and so on and so forth. I think a poor way to interpret SafeGraph data is that it tells you all of the information that's happening at a particular Starbucks. I think it's just unrealistic in that way. And so I'd say the data are very useful for modeling and for inferring larger patterns in the data, especially if you aggregate those types of variations of noise. And you do things, or you can do things like outlier filtering and so on and so forth, like lots of ways to get value of the data in that way.
Awesome. Any other questions from the audience? I know some of you might have already used some part of the SafeGraph data. So from your experience, if you have any other questions related to any of the data sets. Okay, so if not, we always have that Slack channel, and like Jeff and James mentioned, there's the SafeGraph community where you can also post those questions. And I think for the data, it's really nice right now as academians, we can use those data for free. So there's a lot of fun things that you can do with the data, a lot of great potentials. So thanks, James, Jeff, Eugene, and Michael a lot for the great talk. So maybe now we can take a short break before we continue on to our next talk, which will be about 10 minutes. So again, thank you very much, guys. So really nice talk.
Okay, thanks for the opportunity.
Thank you very much.